This question, a thin rod is rotating about a pivot on a smooth horizontal surface on another identical rod is initially kept at rest. Just before the collision pivot is removed, the rod sticks to each other and overlapping length is equal to x. And we have to find x is equal to x naught, for which system has pure translational motion after the collision. There should be no rotation. And if we choose x is equal to x naught by 2, obviously then there will be rotation. So then we have to find the angular velocity after the collision. So again, this is a question based on collision. Initially it is rotating. This system is kept on a horizontal surface. You have to keep in mind that this system is kept on a smooth horizontal surface, so gravity has no effect. So this rod was initially rotating with about this hinge, and just before collision this hinge was removed, and the rod will continue to move with angular velocity omega. There will be no such kind of impulse due to removal of this hinge, so this rod will still rotate like this just after removal of this hinge. So still it is rotating with angular velocity omega. At some angular position this is rotating with omega, and at this location, at this situation just before collision, it is also rotating with omega, since there is no torque on this rod when it was rotating like this. So about hinge there was no torque initially. After removal of this also there is no torque acting on this rod, so this is again rotating with omega. Just before collision, this is the situation. This rod is at rest and this rod is rotating with angular velocity omega. So obviously, since pivot is removed, there is no external force now, and obviously there is no external torque now, so we can conserve the linear momentum also, we can conserve the angular momentum also for this collision. For angular momentum, we will choose a convenient inertial point, and that inertial point definitely we will not choose a material point here. Material point को select नहीं करते हैं, ये पहले भी मैंने कई वीडियोस में डिस्कस किया हुआ है, क्योंकि material point के पास में कुछ velocities होती हैं, तो velocities उनके फ्रेम में करने के लिए हमें velocities का adjustments करना पड़ेगा. We have to adjust the velocities according to that material velocity, material point velocity. So if we choose this point, so we will choose a point in space which coincides with this point and which will be the inertial point. So we will not choose the material point in conserving angular momentum. And there is no problem in conserving linear momentum, because we don't have to choose any point about which the linear momentum is to be conserved. So linear quantities are exempted from this. In linear quantities we don't have to think about a point, we just have to think about the direction in linear momentum cases. But in angular momentum we have to just think about the points, a convenient point. So I will do this question by two methods, by taking 2 points. First I am taking the center of mass, this center of mass of this whole system. I am taking center of mass of this whole system, and about that I will conserve the angular momentum. So where is the center of mass of this whole system? Obviously this length is equal to L minus x here, and this length is also L minus x here, and this is the overlapping region. So and both rods are identical, both masses will be equal, lengths are equal. So obviously the center of mass will be of this complete system will be at the midpoint of this overlapping region. So midpoint of overlapping region is the symmetrical point for both the rods in this particular situation. So midpoint will be somewhere here. This is the midpoint of the overlapping region, and this will be at a distance from here. This is L minus x, and this distance will be x by 2. So this is the location of center of mass of this whole system. Center of mass of this whole system will lie on this line. Just after collision, what is the situation? Let us draw. So just after collision, the situation, just I am drawing a system just by a line here. Just after the collision system is something like this, and system has to move with no omega, omega will be 0. So just after collision there is no omega, omega is 0 now. Just after collision omega is 0 and we will have only the velocities. All the points on this composite system will move with same velocity, so that omega is 0. I'm just showing the velocity of center of mass here. This is center of mass of the system, and this distance will be, this is L minus x plus x by 2. So this will be L minus x by 2. So this is the distance of center of mass. Conservation of angular momentum about CM of the system. I am applying this concept, and this is my method number 1. Conservation of angular momentum about CM of system. So conservation of angular momentum. Just quickly revise how we write the angular momentum in general motion, in which there is translational motion and rotational motion both. So let's say this is a body, this is the center of mass, and this is the velocity of center of mass, and we are interested in writing the angular momentum about any point like this. This is the r vector of center of mass from this point. So one term will be translational term and one is rotational term. This is rotating with angular velocity omega. So for translational term we can just drop perpendicular from this particular location. So I am dropping this perpendicular, this is r perpendicular. So one term will be mvcm multiplied by this r perpendicular, and we have to see the direction also, it is clockwise, anti-clockwise, in which sense this angular momentum is. In this particular situation, in this diagram, this is clockwise, so this is clockwise, and next term will be independent of the point chosen. Whatever point we choose, whichever point we choose, this term is going to be independent of that. This is simply ICM into omega. Many students commit mistake in this term. They take I about this point, so this will be the mistake. This can be the mistake in this particular term. So this is ICM into omega, and this term is also clockwise because I am taking omega as clockwise. If both the terms are clockwise, then you can just drop this clockwise and just take sign convention. Both will be positive. If one is anti-clockwise and one is clockwise, then one term is positive and one term is negative according to the sign convention you have adopted. Okay, so we have to write this. So L initial will be initial angular momentum. Initial angular momentum. This is the center of mass of this whole system, and initially, just before collision, this rod is at rest, and this rod is moving with angular velocity omega, which was about this point. So this point at just before collision, this point is at rest, and this point is velocity some omega into r, omega into r, omega into what kind of velocities this point will have. So all these points will have different velocities with the zero velocity of this point. So L initial, in writing L initial, there is no angular momentum due to this green rod because it is at rest, and this red rod is moving, so angular momentum will be due to this rod only. And because this system is not behaving like a rigid body just before the collision, we have to write the angular momentum contributed by them separately. If now in this particular situation, just after collision, the system is just like a single rigid system, so we can just write the angular momentum of this combination directly. But in this particular situation, we have to write the angular momentum separately due to this red and due to this green, because both are not rigid system just before the collision. So contribution due to green will be 0. Just you have to write the contribution of this red, and for this red, its individual center of mass will be somewhere here. This is the individual center of mass. I am representing this individual center of mass by C1. Similarly, you can see for green also, this its individual center of mass will be somewhere here. This is the individual center of mass. Let's say this is C2. So this is the individual center of mass of this red rod. So L initial for this red one. only contributed due to this red. So let us write in red, and you have to keep in mind these two terms. So this point, and this is the center of mass of the whole system, but this is not the center of mass of this red rod, and this is C1 is moving with velocity of what velocity C1 is moving? This is moving with velocity of omega L by 2. So just compare from this example. This is the point about which I am going to take the angular momentum, and whatever system this is, this center of mass of this system is moving with VCM and it is rotating with omega. So this is a point about which I am going to write the angular momentum, and while writing about this for the red rod, center of mass of this red rod is moving with velocity omega L by 2. So one term will be, let us take the mass equal to m. One term will be mvr term, and that in that mvr term, this will be the r, this will be your r. So this distance is going to be the distance r. So let us see what this distance can be, and the other term will be ICM into omega. I am spending so much time because many students commit mistake while writing these expressions. So these expressions should have been written very clearly, very carefully. So this distance can be calculated like this. This total distance from here to here, this is the center of mass of the system. This total distance here, I have written this distance as L minus x by 2. So this is L minus x by 2. So this is L minus x by 2, and this distance, this is the center of mass of this rod. So this is L by 2. So total is L minus x by 2, and this is L by 2. So just minus these two distances. So if this distance is, let's say, r, so this r is going to be, total is L minus x by 2 minus L by 2. So this is going to be L by 2 minus x by 2. This is the r. Just keep in this expression. Now mvr, जो mvr का यहाँ पर सेंस होगा, this is the r vector here, r cross v, this is anti-clockwise. So this term has anti-clockwise sense. Angular momentum due to this VCM will be anti-clockwise, and omega is clockwise, so this term will be clockwise. So I am taking clockwise term as positive and anti-clockwise term as negative. So clockwise term as positive, anti-clockwise term as negative. So clockwise will be contribution of omega, and that will be ICM into omega. So ICM, what CM is this? This CM is the center of mass of this rod. I am writing angular momentum of rod about this point, which is CM of the system, and this C1 is the CM of this rod. So this is ml square by 12 into omega. This term has clockwise sense. I am taking this term as positive, and another term is anti-clockwise, so I am taking that as negative. So this is mvr. What is v here? V is omega L by 2. And what is r here? R is L minus x by 2. So this term is anti-clockwise. So that's why I have put in negative side here. Now coming to L final. Now just think of this complete system as a rigid system, and this rigid system has no angular velocity. That means we don't have any term ICM into omega. So there is no term of ICM into omega in L final. And what about the first term? The first term, this is mv into r perpendicular. R perpendicular distance from this point to this line of action. And obviously, if we are writing about the center of mass only, then the velocity is passing through the center of mass. So r vector will become 0, r perpendicular will become 0. So the translational term is 0 because r is 0, and the rotational term is 0 because omega is 0. So L final, if I am writing about this point, then L final will be 0. So L initial is equal to L final. This is our equation. L initial is equal to L final. So from L initial is equal to L final, you can just keep this 2 and omega will be cancelled, m will be cancelled, and you will get the answer easily. X is equal to 12 by 3. So this is the answer for the first part. Now in method number 2, we will conserve the angular momentum about initially pivot point A. So I am going to conserve the angular momentum about this point A. So what is L initial and L final about point A? So L initial, obviously the angular momentum will be contributed due to this red rod only, and just before collision this point is at rest. So if this point is at rest, so we can directly write about this point in just single term, I into omega, just like we write angular momentum about a hinge point. Like that I can write here I about this point A, I about this axis which is passing through A into omega. Otherwise, if you have confusion, then you can write the two term, one rotational, one translational, about this point for this red rod only. So for red rod only initially, just we can simply write it as, what is I about A? This is ml square by 3, and what is angular velocity? This is omega. So ml square by 3 into omega, this is L initial, and obviously this is in the clockwise sense. This is clockwise. What is L final? So just write L final. In L final, there is no omega. Obviously there is no omega. Omega is 0 here. So omega is 0 here, and this complete rigid system is moving translationally. All the points are moving with the same velocity, and here momentum is conserved. Initial momentum is equal to final momentum. Momentum is conserved. So let us first find the velocity here. All the points are moving with the same velocity. Obviously all the points are moving with the velocity of center of mass of the system. This is the center of mass of the system, and it is moving with VCM. So let us first find the VCM, then only we can write the L final. So before writing L final, I am calculating VCM. For that, P initial is equal to P final. P initial only due to red rod only, this green rod is at rest. So P initial is m into velocity of center of mass of this rod, this red rod. So its center of mass is somewhere here. This is C1, and this distance obviously L by 2. So this is contributed due to this red only. So this is m. VCM is omega, center of mass of this C1, m omega L by 2. What is P final? So for P final, we can simply write it as total mass of the system, because this is a rigid system whose center of mass is moving with velocity VCM. So this is 2m into VCM. From here we can find the VCM. VCM is omega L by 4. So for writing L final, now I am going in this expression. So L final about this particular point. Obviously there is no term of omega here. There is no term of omega. So how to write this L final? L final due to this combined rod. So for writing L final, just we have to write the MVR. What is R here? R is L minus X by 2. So what is M here? M is 2M. This is 2M. What is V here? V is VCM. This is omega L by 4. And what is R? R is L minus X by 2. Again this term will be clockwise, so just we can equate this two term. L initial is equal to L final and solve the problem. So L initial is equal to L final. This is simple equation, and this equation will again give the same result. X is equal to 2L by 3. So this is the value of X here. In writing L final, you can also write L final as two separate terms. You can separately write for red, you can separately write for green also. So I am writing L final as L due to this rod and L due to green and red rods separately. If I am going to write due to red 1, so due to red 1, just concentrate on this rod. This rod is not rotating after collision, and I am writing about this point. So this point, and just I am writing for this red rod. So from this point, center of mass of this red rod C1 is at a distance L by 2, and again it is moving with the same velocity. All the points are moving with the same velocity VCM, which is omega L by 4. So I am writing omega L by 4 only. So M omega L by 4, and distance will be L by 2. So this is the term contributed due to red one. The term contributed due to this green one, mass velocity is again omega L by 4, and just have to find the distance. So this distance was equal to L minus x. So this was L minus x, and its center of this this green one will be here, somewhere here, C2, and this C2 is at a distance L by 2 from here. So this total distance will be L minus x plus L by 2. Just equate L final is equal to L initial, and you will get the same answer, x is equal to L by 3, from here also. Now for the next part, x is equal to x naught by 2, and now x is equal to L by 3. I am taking center of mass of the system to write my equation of conservation of angular momentum. So now finally the rod has both kind of motion here. Rod has omega and rod has linear velocity both in this particular situation. So about center of mass of the system, I am going to write about center of mass of the system. So what is L initial? L initial I have already written in the previous solution. So just I can borrow this from here. L initial is ml square by 12 into omega. This is clockwise. I am taking clockwise as positive, and m omega L by 2 into L minus x by 2. So this complete term I am borrowing from here. So L initial, if I am going to write about center of mass, so L initial will be ml square by 12 into omega minus of m omega L by 2 into L minus x by 2. This is L initial. What is going to be L final here? So for L final, again keep in mind how to write the angular momentum terms. So how to write angular momentum terms here in L final? I am going to write about center of mass, and if I am going to write about center of mass, if this is my system and I am taking angular momentum, writing angular momentum about this center of mass of this system, so MVR term will not come because R will be 0. Only the term about center of mass will be ICM into omega. So I am concerned with the angular momentum about center of mass, then ICM into omega. This omega will be omega dash finally, and ICM, I have to calculate this. I have to calculate the moment of inertia of this complete system about this center of mass of the system. So the red will, if I calculate the moment of inertia of the red one, then green one will also be the same because of the symmetry. So just I am calculating the moment of inertia of the system about center of mass. I am multiplying with 2 whatever expression I am calculating for the red one. So 2 multiplied with the moment of inertia due to red one, and for that I have calculated some distances also. I have shown some distances also. Obviously this is L by 3, so this is L by 6, this distance is L by 6, and upper distance will be 2L by 3, and between center of mass and C1 the distance will be 5L by 6 minus L by 2, where 5L by 6, from where 5L by 6 is coming, 5L by 6 is coming from here. It is, this distance is 2L by 3 and this is 2L by 6. So 2L by 3 plus 2L by 6, 2L by 3 plus L by 6, this will be the 5L by 6. And from 5L by 6, this total distance is 5L by 6. From this I am subtracting L by 2. So it will give me the distance between C1 and CM. So between C1 and CM the distance is L by 3. And I need this distance to write my ICM. So let us come to ICM. This ICM will be moment of inertia of the red one about its own center of mass is ml square by 2. I am using parallax theorem. So moment of inertia of red rod about its own center of mass is ml square by 12 plus m into this distance square, ml by 3 square. So this moment of inertia, this total moment of inertia, 2 into 7 ml square by 36, and this will be 7 ml square by 18. This is the total moment of inertia of this system. And just now L initial is equal to L final. Just simply L initial is equal to L final now. So L initial, this is equal to L final. This is your L initial, and this is for L final. Just you have to write 7 ml square by 18 into omega dash. Just equate this two, and you just write x is equal to, here x is equal to L by 3. So easily we can find the final omega dash. Final omega dash is coming out to be 3 omega by 14. So this is the final answer. Method number 2, about initially pivot point A. So L initial, already we have calculated this. L initial, this is ml square by 3 into omega. So this is our L initial, and this is in the clockwise sense, and clockwise I am taking as positive. What is L final here? So for L final, just you have to keep in mind this system as a rigid system, and I am writing about this point. Let us assume the angular velocity is omega dash in this sense only, in the clockwise sense only, let us assume. So L final, for L final we have to write two terms, one is translational and other is rotational. So this translational term, how it will go? This translational term is again, if I am writing about this point, this translational term, this is your r vector, r cross v, this is again clockwise. So this term is again clockwise. So this term is going to be clockwise here. So L final, this is mvr term, mass is 2m, v is omega L by 4, vcm is omega L by 4, and r, if you calculate this distance r, so this will come out as 5L by 6, 2L by 3 plus L by 6. So 2L by 3 plus L by 6, this is 5L by 6. So this is this term, and other term will be ICM into omega. You just have to keep in mind this is ICM into omega dash. This term is clockwise. ICM already we have calculated in the previous solution. This is 7 ml square by 18. So no need to calculate again. 7 ml square by 18 into omega dash. So just equate this to L initial is equal to L final, and you will get the same answer of omega dash, 3 omega by 14.